Well, you see, what happens in a Bose-Einstein condensate? A macroscopic number of them, number of particles, are in the ground state. Let's say.
Ground state is a coherent state, right? So ground state is a coherent state.
Yeah. They all have the same wave function. A macroscopic number of particles have the same wave function. Also keep in mind that the Bose-Einstein condensation basically appears when n lambda cube is around 1. Which means that, you see, lambda is basically the size of the quantum mechanical wave function of the atoms. So this basically tells me that the wave functions are now overlapping. So when you get the Bose-Einstein condensate, when the wave functions start to overlap. Now we have just 2 weeks this week. We will have a lecture also on Wednesday. We will have a lecture also on next Monday. Wednesday is a holiday. Well, let's see how much we cover. I would like to cover the so-called van der Waals gas. Well, this is an example of a phase transition. I would like to look at white dwarfs. Well, this is just an application of what we will study now for the Fermi, and we can model the white dwarfs as a Fermi gas, an ideal gas of fermions. And well, if we can finish this on Monday, I won't have any extra lecture. But if I cannot cover the van der Waals gas, I would rather have it, I don't know, maybe Friday. But we will talk Monday. On Monday, when we can go over them. So now let's start the gas of fermions. We will basically repeat what we had done for the gas of bosons. So we have more or less the equations look almost identical, except an assign. We have the total number would be given by sum over all single particle states. Of 1 over e to the power beta epsilon minus mu plus 1. Remember, in the boson case, it was a minus 1. Now we have, that's a plus 1. We have the energy of the system, again, sum over single particle states, epsilon over e to the power beta, epsilon minus mu, plus 1. The pressure of the system, PV over KT, is just the logarithm of the grand partition function, which will be sum over, again, single particle states of logarithm of 1 plus e to the power minus beta, epsilon minus mu. So what we need to do now is solve the first equation for mu, the chemical potential, and put it in the other equations to find the energy, the pressure, etc. And then, of course, we will look at, we won't be able to solve it exactly. We will look at what happens at high temperatures and what happens at low temperatures. Now, but before going into the details, let's look at this function and try to see what is expecting us. Yes, let me call this an Fermi-Dirac of epsilon. Now, if you remember, when we were looking at the Bose-Einstein gas, when epsilon was equal to mu, that exponent just becomes 1. We had 1 over 1 minus 1, which diverged. So we couldn't have the case epsilon is equal to mu. But that basically told us that since the energies are almost continuous from 0 to infinity, that told us that mu had to be less than all other possible energy values, and hence had to be negative, so that this number doesn't diverge. But now, if you just put epsilon is equal to mu, you get 1 over 2. When epsilon is equal to mu, again, that exponent is 1, so we have 1 over 1 plus 1, 1 over 2. So the average number of particles in the state with energy epsilon is equal to mu, if there is such a state, would be just 1/2. So there's no problem having epsilon is equal to mu, and hence mu can be positive, negative. We don't really have any restriction over here. Now, let's look at what happens, for example, when t goes to 0. Well, when t goes to 0, beta diverges. So the Fermi-Dirac distribution for epsilon larger than mu, you see, if epsilon is larger than mu, that means epsilon minus mu is positive, beta is infinite, so that's the exponent of infinity, which is infinite, so we have 1 over infinity, which is 0. And for epsilon less than mu, well, then epsilon minus mu is negative. We are multiplying a negative number with infinity, that is minus infinite. The exponent of minus infinity is 0. So we have 1 over 1, which is 1. So it's basically the step function. And if you like, when epsilon is equal to mu, it is 1 over 2. This is when t goes to 0. Of course, this is here. We have the chemical potential at t is equal to 0. So what happens? This is our distribution function. Well, well, so that number is usually given a special name called the Fermi energy. But you see, Fermi energy is positive. So at least at low temperatures, the chemical potential can be positive. In the case of bosons, at low temperature, it could be at most 0. But in the case of fermions, well, it's a positive. It has to be a positive number. And typically, this Fermi energy is of the order of electron volts, which is, by the way, of the order of 10 to the power 4, 10 to the power 5 Kelvin. So, for example, if you consider the metals, well, there are many electrons moving around. So the electrons in a metal, at least those who are moving around freely, they can be approximated as a Fermi gas made up of electrons. But since the room temperature is just 300 Kelvin, 10 to the power 2 Kelvin, they are very cold. So room temperature for electrons in this metal is, they are basically a fermionic system at very low temperature. You see, when we looked at bosons, room temperature was a very high temperature. In order to create a Bose-Einstein condensate, we had to, one has to cool it to sub-Kelvin temperatures. But for fermions, the room temperature is very cold. So now this is what you will see at 0 Kelvin. Well, that is expected. Just like in the case of bosons, the fermions now go to the ground state, to the lowest state possible. But the problem with fermions is that all the bosons could go to the ground state. But for fermions, there can be only one fermion per state. So they cannot all go to the same state. So what happens is, first you fill the ground state, then you fill the next state, fill the next state, and it's just, you just pile up electrons in a sense. So if this is the ground state energy, the next electron goes here, the next goes here, the next goes here, etc. And you fill all the states up to some given energy, and this is the energy of that state is what we call the Fermi energy. And as I said, since they are of the Fermi energy of the order of 1 electron volt, it's a very energetic system. Now, what happens if you turn on the temperature So just imagine, if you like these metals, there are all these electrons just moving around. There is the nuclei which are vibrating. The thermal energy of vibration of the nuclei is of the order of kT. But kT is very small. When the nuclei collides with the electrons, let's say, they can transfer at most an energy of kT. Or even when the electrons are colliding with each other, the typical thermal energy will be of the order of kT. But kT is somewhere over here. Let's say this is 2 kT. Now, if you consider an electron at this level, if it absorbs this energy kT, if it tries to absorb that energy kT, what it will do is it will try to go to some state over here. But that state is already occupied. So that electron cannot absorb this thermal energy. Only electrons close to the Fermi level. So for example, this electron over there, when it absorbs an energy kT, it will basically move over here. And there is an available state over there, so it will be able to absorb it. So what this basically means is when you are considering thermal motion, thermal energy, only the electrons within these energy levels will participate. The other ones cannot absorb the thermal energy. They are frozen. So in fact, this was the answer to one of the puzzles. If you look at this metal, well, we have the ions. We can just treat them as a compact object moving together. And then we have the electrons. We have almost as many electrons as the ions in the metal. And equipartition theorem told us that every degree of freedom basically contributes kT over 2. So the electrons should contribute as much as the ions. But experiments told us otherwise. It was as if the electrons didn't contribute at all. And basically the reason is room temperature is very low. And hence the electrons are frozen, if you like. Now, as you increase the temperature, what will happen is this step function, you see, when the temperature, you start increasing it, only the electrons at the close to the Fermi level will shift to higher energies. So there will be less electrons close to the Fermi level but below it, and more electrons close to the Fermi level but above it. This will be the distribution you will get at first. And then if you increase the temperature further, this will be the temperature. This is what you will get eventually. You see, this is 1/2. Which basically tells me that the chemical potential starts from a positive value. It gets smaller as you increase the temperature. Eventually it can become negative. And in fact, that is what we would expect, because at very high temperatures, we would expect everything to behave almost the same, the bosons, the fermions, and Maxwell-Boltzmann particles. And we already know that the bosons have a negative chemical potential at high temperatures. And in fact, the fermions will also have a negative chemical potential at high temperature. They start from a positive value, and you will eventually have a negative chemical potential. These are the things that we will eventually see. Again, if you remember our discussions on the Bose-Einstein condensation, we said that, okay, we can convert these sums over single particle states to integrations over the energy. But we had to be careful about the ground state, because that single state, although the density of states of that single state is 0, it can contribute significantly. So we had to separate out the ground state, because in the ground state we could have a macroscopic number of particles. Well, we don't need to worry about that in the case of the Fermi-Dirac distribution, because in the ground state we can have at most one particle. Well, if you calculate this, consider the spin degeneracy of the electrons, well, you have 2 particles. There is no way you will have a macroscopic number of particles in the ground state. And as usual, well, let's start with the number of particles. This is sum over single particle states of 1 over e to power beta epsilon minus mu plus 1, or we can write it as sum over single particle states of 1 over z inverse e to power beta epsilon plus 1. Z is again the usual definition. It's the same definition whether you are looking at bosons or fermions. It's the so-called the fugacity. And that sum over single particle states, we can write it as an integral over possible momenta and coordinate over h cubed. Well, this, I mean, how many of you are studying condensed matter physics?
I'm going to talk about scope.
Hmm?
I'm going to talk about scope.
No, we won't have time for that. But still, for example, if you are looking at electrons, you will be talking about two-dimensional electron gas. You basically sandwich electrons between various semiconductors, create a two-dimensional potential. Well, in that case, the electrons are allowed to move only along that potential. In that case, you don't have this d cubed p, d cubed q, but you have d squared p, d squared q. So you have a two-dimensional gas. You can have a one-dimensional gas where you have, instead of 3, just 1. Of 1 over. Well, then we will basically do the same tricks, let's say. The Q integration over Q gives me the volume. The energy depends only on the magnitude of momenta, so we can integrate over the directions of momenta. That will bring a 4 pi. We have dp, p squared, divided by z inverse e to power beta epsilon plus 1 from 0 to infinity, divided by h cubed. Then let me also add the g. G is the degeneracy for a given momentum. For example, if you are looking at an electron gas, the electrons for a given momentum and coordinate, they can be spin up or spin down. So there are two states for a given single particle state. So that is what G is. And typically we prefer to write this as an integral over the energy. So if energy is given by p squared over 2m, dp is square root of 2m over 2 square root of epsilon. So the number of particles is v 4 pi over h cubed. And then we have 2m to the power 3 over 2 divided by 2. So small n, which is capital N over V, this is given as G times 4 pi, no, 2 pi, 2m to the 3 over 2 divided by h cubed, 0 to infinity the epsilon to the power 3 over 2 minus 1 square root of epsilon, divided by z to the minus 1 e to the power beta epsilon plus 1. And let me divide by gamma 3 over 2, multiply by gamma 3 over 2. And all this factor over here is 1 over lambda cubed, lambda being h over square root of 2 pi mkt. This is the thermal wavelength. Well, this we had already done also for the bosons. Basically the same treatment. We are calculating the density of states. And so we have n lambda cubed over 3. This function is defined as f 3 over 2 z. And the density of states is basically V over lambda cubed divided by 1 over gamma 3 over 2 square root of epsilon. So any questions up to here? Now we have a different function. Remember, before we had g, okay, these functions f nu of z, they are defined as 1 over gamma nu from 0 to infinity, the x to the power nu minus 1. Sorry, there is one more change I should do. E to the power x plus 1. Now basically I just redefine beta epsilon as x, then the epsilon square root of epsilon divided by kt to the power 3 over 2 is just dxx square root of x. And so this is the correct expression still.
And is there 3 on the lambda cubed?
This is g.
Okay.
That is not 9. Just last month I learned the proper way of writing 9. Because this is my 9. This is my g. So I was told that the proper way of writing 9 is this one.
Can you try and
Q is easy. I can distinguish Q and 9.
Maybe
try calligraphic Q?
maybe has the
Yeah.
tail of 9.
I was teaching high school teachers a couple of months ago, and at one point I wrote G. At the next line it just became a 9. So I couldn't read my handwriting.
Isn't it easier to define x as beta times epsilon minus mu?
Well, you see, the problem is if I define x in that form, and then chemical potential goes to the integration limits. And I don't want to deal with unknown functions in the integration limits. So this is one of our expressions. And in fact, we have to solve that equation for z. But before trying to solve for z, let's calculate the other quantities. On one hand, we have u is equal to sum over single particle states of epsilon divided by z to the power minus 1 e to the power beta epsilon plus 1, which becomes v over lambda cubed 1 over gamma 3 over 2, the epsilon square root of epsilon from 0 to infinity times epsilon over z to the minus 1 e to the power beta epsilon plus 1. I just straight away use this density of states. And again, if you just make a change of variable, beta epsilon is equal to x, this will be v over lambda cubed 1 over gamma 3 over 2 kt to the power 5 over 2 f 5 over 2 of z. times gamma 5 over 2. Well, remember, f5 over 2 in its definition is that integral after that change of variables divided by gamma 5 over 2. So I'm just multiplying with gamma 5 over 2. So these cancel. I have 3 over 2. So this is u is 3 over 2 v over lambda cubed kt to the power 5 over 2 f 5 over 2 of z. There is something wrong here. Do we see what is wrong here? Huh? No, there's something
You already
Fundam-
have lambda.
Hmm?
Is the power of t?
Is it?
Is it power of t?
Is there something fundamentally wrong? You see, whenever you make some derivation, especially if you are jumping some steps as I did now, the first thing you should check at the end of your computation, even while you are doing the computation, the units. The units should be correct. Because f functions, the way we define it, they are dimensionless. They don't have any units. V over lambda cubed is dimensionless. They don't have any units. So this kt has the dimension of u, but here I have kt to the 5 halves. So there is something fundamentally wrong over here.
The other factors are already contained within lambdas to lambda cube, right? So
Yes, sir.
there should be a single kt left.
So if I write it properly, g is 4 pi v over h cubed times 2m to the power 3 over 2. This is 2 square root of epsilon. This is g of epsilon. So if I put it over here, two pi v over h cubed 2m to the power 3 over 2. U is 2 pi v over h cubed 2m to the power 3 over 2. If we make that change of variable, we will have kt to the power 5 over 2, and then 1 over gamma 5 over 2 times f 5 over 2 of z. Now I can use the definition of lambda, which will be 2 pi m h over 2 pi m kt to the power 1 over 2. So this will be u will be v over lambda cube. Then I have a single factor of kt. And what else is missing? 1 over square root of 2 pi. You see, 1 over lambda cube brings me a 2 pi to the power 3 halves. But I only have a single factor of 2 pi. I should cancel square root of 2 pi. And then 2m to the power 3 over... No, sorry. 2m to the power 3 over 2 is already there. Kt to the 3 half is already there here. 2m is already there. Here I have a pi to the power 3 halves in 1 over lambda cube, but in the u I have 2 pi. This is U. Well, this ratio is 3/2. If you look up the value of gamma 5/2, that ratio is 3/2, so we end up having U is equal to 3/2 KT V over lambda cubed F 5/2 of Z. But let me check this one in the break. And we also have, well, there's a factor I forgot, the degeneracy, G. This is my U. Now, before you go for a break, let's also look at what PV over KT is. This was again sum over single particle states of logarithm of 1 plus Z e to power minus beta epsilon, which I can write as some integral over the energies, G epsilon, logarithm of 1 plus Z e to power minus beta epsilon from 0 to infinity. Now, what I would like to do is convert the logarithm, express this in terms of the Fermi-Dirac distribution. So I need to take I have to somehow manipulate this integral so that I take the derivative of the logarithm with respect to energy. That will give me the Fermi-Dirac distribution. And in order to do that, just note that G epsilon, which is proportional to epsilon to the 1/2, I can write this as the derivative of G epsilon times epsilon with respect to epsilon. That product is proportional to epsilon to the power 3/2. So if I take the derivative, it brings down a factor 3/2. So let me just multiply it by 2/3. So PV over KT is equal to this integral of 2/3 d by d epsilon of G epsilon times epsilon of this logarithm. Now if we do integration by parts, the boundary terms will not contribute. I will only have 2/3 from 0 to infinity minus 2/3 from 0 to infinity d epsilon G epsilon epsilon. Now the derivative of that logarithm is, with respect to epsilon, is minus beta times Z e to power minus beta epsilon divided by Z e to power minus beta epsilon 1 plus Z e to the power minus beta epsilon. So these minus signs, they cancel. We have 2/3 KT 0 to infinity d epsilon G epsilon epsilon over Z inverse e to power beta epsilon plus 1. This is PV over KT. So PV is 2/3. Well, but if you look at that integral, that is nothing but the total energy. You see, whatever the temperature is, PV is always equal to the 2/3 the internal energy of the system. Whether you are at high temperature or low temperature, it doesn't matter. PV is equal to 2/3 of U. So any questions up to here? Now, the only thing we did up to here is, okay, we have this result. And this, we have these three results. And we will try to understand what these results tell us. Well, by the way, this U, I can also write it as, let's say, U over N is G times 3 over 2 KT, 1 over N lambda cubed. Let me put the G also over here, of F5 over 2 of Z. But this ratio is nothing but 1 over F3 over 2 of Z. So U over N, the energy per particle is 3 over 2 KT, F5 over 2 of Z divided by F3 over 2 of Z. And when Z is small, we will see in the next hour that these F functions just become Z for small z. We'll find their Taylor expansion as a function of Z for small z, and whatever the nu is as Z goes to 0, this is just Z, so that ratio is 1. We basically recover the classical result as U is equal to 3 over 2 nkt when Z is small.
Are we still talking about the low temperature case?
No, I mean, you see, I talked about the low temperature case up to here, and saw what happened as we increase the temperature. Now, starting from here, I'm just looking at generally what happens. You see, none of the derivations in these steps, I mean, what I did was, these are my general expressions for the fermions. They are valid whether we are at low temperature or high temperature. I'm just replacing the sum over single particle states as an integration over the energies. And that is how I obtain these results. In fact, these three of them. They are valid at any temperature. And in particular, we have, well, this one is again valid at any temperature. But here, I said that if Z goes to 0, since these functions f nu of Z, they just become Z for small values of Z. For small values of Z, we recover U over N is equal to 3 over 2 N. U is 3 over 2 nkt. Now, what does small z mean? Well, if z is small, you see, this is our definition of z. If z is small, that equation tells me that z is of the order, z is equal to, approximately equal to n, the number density times the Broglie wavelength cubed. And that number should be small for us to recover the classical limit. Well, you see, that number is small. Z would be small if n lambda cube is small. That is, either you have a very rarefied gas, you have a few number of particles per volume, that's small and small, or lambda might be very large, the thermal wavelength. And remember, thermal wavelength is proportional to 1 over the square root of temperature. So lambda is very small, means that temperature is very large. So although here I assume that z goes to 0, so what does that mean physically? When I ask this question, what does small z mean? Physically, I'm led to the conclusion that if z is small, that is a rarefied gas at high temperatures. That is our classical limit. I don't start by saying that, oh, I have a high temperature, so I recover the high temperature, the classical result in high temperature. That's not what I'm saying. What I'm saying is I recover the classical result for small z, small chemical potential, which means high temperature.
Or even very rarefied gas, right?
Yes.
So, yeah.
Well, you see, when you are talking about the temperature, what does high temperature mean? One is, at least in the case of the fermions, much higher than the Fermi energy. That would be the high temperature limit. But now we have another criteria for high temperature. It should be high enough such that n lambda cubed is small. That's another definition of high temperature. In fact, this second definition of high temperature, that is Fermi level, doesn't exist in classical limit. So you cannot, if you are looking at the classical limit, it just doesn't, I mean, saying that it's larger than the Fermi energy doesn't really tell me much. Doesn't tell me whether I'm close to the classical limit or not. But saying that n lambda cubed should be much less than 1. Well, first of all, it tells me that the atoms should be separated. Remember, the lambda is nothing but the size of the wavelength, size of the wave function. So the wave function of these different atoms shouldn't be touching each other. And that happens when either we have a very rarefied gas. Yes, let's say that in this room, let's say you have 5 atoms. Their wave functions will not touch unless you are at very, very low temperatures. Or you are at a very high temperature such that the wave functions are small.
So, having low or high temperature means, I guess, that there's a scale, energy scale of the system, as if we have a harmonic oscillator in the case of harmonic oscillator, and that this is nothing but the Fermi energy, right?
Well, you see, here now we have a system that has 2 different energy scales, not just one, 2 of them. One is the Fermi energy.
But it's also a very variable from system to system.
Sure. The Fermi energy is a typical energy scale for this system. Well, it's variable, but for macroscopic objects, it's typically of the order of electron volts.
What about neutron stars?
We will come there. The second energy state level that will be important for us will be given by this condition, n lambda cube. This defines whether this is much less than 1 or much larger 1. This also defines another energy scale, another temperature scale. Now the question is, are these scales the same, related somehow? We will see. At least this n lambda cube, this criteria of n lambda cube being much larger than 1 or much smaller than 1, it appears in every system. Or in fermionic systems, in bosonic systems, we basically have the same. I mean, in bosonic systems, we basically had the same equation. The only difference being we didn't have the F3 halves, but G3 halves. And the only difference in their definition is the sign of the 1 in the denominator here. So we basically have the same problem. But now, at least for the time being, it seems that we have 2 different energy scales.
How's the second energy scale in the case of bosonic system?
If you have a Bose-Einstein condensation, T criticals defines another energy scale of the problem. Now, we still didn't look at whether these 2 energy scales, one, the energy scale fixed by n lambda cube is equal to 1, let's say. This defines an energy scale. Energy read temperature. At the same time, epsilon Fermi is another energy scale. But of course, I mean, okay, we have 2 different, it seems that we have 2 different energy scales, but maybe they are related somehow. They might be the same energy scale. We didn't look at that yet. We will see that. Okay, let's give a break now, 10 minutes, and then we will continue after the break.